my goal today really is to give you a feel for the code and what you need to do and what the possibilities are. The technical stuff comes with practice and applying it. But if you can get a feel and know what's there and what to expect and how to apply it in a way that kind of makes it efficient for you to do so, that's what I'm hoping we can get out of this presentation today. First, we'll just cover some preliminaries and some basic concepts so that we're all on the sort of the same fundamental page as to why we even are concerned about wall bracing. And then we'll get into the nitty-gritty of the IRC wall bracing provisions. And then I'm going to walk through sort of a step-by-step accounting procedure. That's sort of the way you would want to apply these so that you're documenting your compliance and making decisions in a sequence that probably is most efficient and would allow you to sort of optimize or make a better decision at a certain stage when it's appropriate to do so. And then I'll talk about some additional resources, some that are available online free, even calculators, the new calculator that implements these provisions. And then as I understand, there'll be a follow-up presentation, then we'll have some Q&A. So sort of a little bit of background on me. I've been involved in structural research, energy, and building science. I kind of got into the energy and particularly the building science stuff from my structural background because I was worried about protecting my structures, and wasn't trusting what was in the codes at the time. So got involved in a lot of structural research and building science research, and the provisions for wall bracing that are in the IRC now were in part based on research I had done on whole buildings and taking engineering technology to the level of being able to predict a whole building system and then reducing that knowledge down into some prescriptive provisions. And I worked with an ICC ad hoc committee to bring that technology into the building code. And on the moisture side, also the provisions that are on the code related to insulation ratios, and how you determine your U factors or your thermal performance while also balancing the moisture performance. There's new vapor control provisions in the code that I've been deeply involved with. So all of this stuff actually fits together. Decisions you make on your structure and how to do it actually affect other performance attributes that you need to be concerned about, like moisture control. So that's the beauty of some of these products that are becoming multifunctional, because they give you all of that in a package. And in many ways, it simplifies the decision making and compliance with the code. But that's another story. Let's focus on wall bracing, and let's jump right in. So preliminaries, the wall bracing provisions in the code, since I think it was when we worked on that in the 2009 edition, and it's been sort of refinement since then, but the big change was in 2009. We did a complete overhaul of the bracing provisions to catch them up to the 21st century, instead of like pre-war housing styles and stuff. And the old bracing methods were simple, but so were the homes, and they were small, and it just worked. But with the newer large homes, large open spaces in the homes, there was a lot of redundancy in the building that had been removed, and we were pressing the limits of good performance. And so that was the genesis of that. But to address that technically accurately and to also provide flexibility, lots of different ways of doing it, so you're not prescribing only one answer in the code, which would not be fair or very cost effective. There's a lot of information in the code, a lot of options. In fact, it's 60% of your wall framing chapter 6 in the IRC. 60% of that, a little better than that, is devoted to wall bracing. So you must know this to use it proficiently. And one of the sort of the fallacies is that just there's a simple solution in there. There's no silver bullet, in the sense that no matter what product you use, no matter how strong it is, you have to use it in the right amount. You have to install it the way that it was intended to be installed. The bracing panels need to be of the correct width or configuration to be able to actually provide the resistance that's needed. And so there's a lot of rules that need to be applied, and they're applied to every single bracing method. Now, the bracing methods may have different properties, and the rules have different values assigned to them for different products, but they're all based on the same principle. So if you use any of the bracing methods correctly, you get a building that has equivalent overall lateral capacity, which is our goal. And then the code doesn't cover all possible bracing options. It couldn't possibly do that, although it has a lot. There are proprietary solutions. And the code, while it focuses on commodity solutions, sticks and bricks and things, the real, it can't stifle innovation by not allowing alternatives. So, you just learned about one alternative that's out there. That is an alternative, a bona fide alternative bracing method that can be substituted into these provisions. Doesn't need an engineer to apply it. It's actually evaluated in a way consistent with these commodity materials so that it can be just plugged into the prescriptive bracing code. The code does not provide solutions covering all conditions of use. In other words, if you're in South Miami, and Hurricane Central with very, very high design wind speeds, it's not that these systems can't be used in that application with the right design. The scope of the code is limited to lower wind regions, sort of moderate hurricane down to sort of what you would consider a normal wind hazard. Same thing with earthquakes. There's certain range of conditions it's designing for, but the most extreme hazards like near fault conditions in California or Alaska, you're going to need an engineer to apply it, just as you would any bracing material. There's design values, and then there's also prescriptive guidance on how to use it if you're not an engineer. So that's the preliminaries, basic concepts for code compliant bracing. We'll just answer two questions: why is bracing needed, and when should I consider doing that? And so the main reason it's needed is to control the risk of building collapse. And obviously that's a life safety concern. Some examples of the characteristics of a building that factor into how much bracing you need to resist a load is, the plan size, the number story and story height of the building are going to affect both wind and seismic load on a given story level. The roof pitch and height and shape will affect the wind load on the building. There's actually an optimal roof slope aerodynamically that would minimize lateral loads. But if you go too low a slope, then you increase your uplift load. So there's sort of an art to building configuration and minimizing your structural loads as a means to be more efficient in your building construction. And then seismic is similarly plan size, your number of stories and story height obviously govern the mass of the building and its inertial response to ground motion. And then the weight is a big issue of materials. So depending on your cladding materials and things, roofing materials, if you're using heavyweight materials, you may get kicked into engineering or some more stringent bracing requirements even in the prescriptive code. So just a heads up on that. The other thing that varies is the hazard itself across the country. So this is a map that sort of combines both seismic and wind hazard. The seismic is your contoured colors across the country there. The red and being the high areas, the green being and yellow being sort of moderate, and then the blue and light color being low seismic. The IRC provisions cover everything except for the reddest colors there, and the wind provisions cover pretty much all. You only need to check wind bracing up through the yellow colors, as shown here on this bar in the IRC. So by meeting wind bracing in those zones, you've covered your seismic. You don't need to do a separate check for seismic bracing and see which controls. That's one advantage in the IRC's bracing provisions, is they don't make you do a double check where you don't need to. So in most of the country, really, 3/4 of it roughly, doing just the wind bracing check in the IRC is all you need. And then you can see here the coastal areas where that's you start to enter into the hurricane-prone region. The rest of the country, the wind speeds might vary, design wind speeds from something less than 90 miles per hour to 115, depending on where you are, but that's considered a fairly low wind region. Before we talk about bracing in detail, I've been to a lot of hurricane and earthquake events, but particularly hurricane events and some tornado events, and done, scientific random sampling of buildings, documentation of performance. And probably the biggest failure you see is wind uplift. Rarely is there a bracing failure unless there's major non-compliances with very little or no bracing, same in seismic events. But for wind, it's the uplift that gets you. And oftentimes the uplift, when the building is uplifted and then moved, like shown in this picture in a full-scale wind tunnel test, it looks like in the end that, well, maybe the bracing wasn't enough. And it was really the uplift load path. Once that fails, it doesn't matter how much bracing you have. So this uplift load path, whether you're using fasteners that are designed to increase the uplift capacity of your framing joints, or using separate brackets and straps, you need to comply with that in the code. And there's provisions in the bracing section to make sure that connection is made, because without that connection, you can go through all the bracing provisions and that will do you no good, because this will be the weakest link. Okay, so when should I consider wall bracing? As soon as possible. It can affect design decisions, maybe tweaking a window location if you're able to do early in the design thing and still keep the architectural design you want, or maybe altering what you do on one wall versus another. It's easy to do at this phase, and then it makes compliance much easier. And particularly if you're doing a model plan that's going to be used repetitively, this fine tuning as early as possible during the design stage is extremely important. Of course, you can kind of get some of that in the back of your mind as you've applied the bracing provisions to get used to this. So as you're doing more of an architectural design, those things are in the back of your mind. It can really save you some headache down the road, or potentially in the field, to have those things all ironed out on your plan. And the code itself, actually, if the building official requires it, but I think it's a good practice. The braced wall lines should be identified on the construction documents for the framer to make sure everybody's on the same page and we don't have a major, error in a building plan. And believe me, they do happen. And having them on the construction documents is your only good hope, basically, of making sure it's done right and giving the inspector something to actually look at to confirm it. So we're going to go down through the nitty gritty of some of the wall bracing stuff. We'll look at, what is a braced wall line? That's sort of the main element where bracing goes, and the wall lines of the building that are declared to be required to be braced wall lines. There's flexibility, and there's an art to what you call braced wall lines. You may need an interior wall line, you may not. And then braced wall panels are what you put in those wall lines. They're actually segments of wall. It doesn't have to be a panel material. It could be a lead-in brace or whatever product or methodology you're using, but there's got to be a segment or a panel of the wall that actually meets the requirements to provide bracing in the braced wall line. We'll look at the minimum required bracing length, then to get the resistance to shear load from wind or seismic that's needed in a wall line, depending on its location and how far away it is from other braced wall lines that are sharing the load that comes to it through your floor and roof diaphragms. And then we'll look at braced wall line construction methods. There's a lot of them in the IRC, and each one has different installation conditions that need to be met. We'll look at minimum length of the individual panels depending on the nature and properties of the panel. You may need to have a minimum 8-foot length, whereas another panel could have a minimum 4-foot length to be qualified as a brace panel, or 3 feet, or maybe even down to 2 feet. So it depends, and those are all criteria you need to meet based on the bracing method you're using. Narrow brace panel methods like portal frames or garage portal frames, where you've got very little wall, but you still need bracing capacity. There's methods in the code for that. Then there are detailing requirements, like what do you do at the end of the brace wall line to anchor it? Because this is conventional construction. There may not be a hold down bracket, but how do we make sure we detail this redundant, repetitive framing system to provide the hold down restraint necessary just through the framing and the corner condition itself, like a corner return panel, to provide restraint so that you can get the shear capacity out of the wall line. So there's detailing requirements there, and flexibility, how you do that. Then we'll talk about connections between the floor and roof. You've got to be able to transfer the load out of the floor and roof diaphragms into the walls so that they're go to the resistance down to the foundation. So those load paths need to be there and properly attached, floors to walls, brace wall lines, and then the brace wall panel support at your foundations. So a lot of stuff to cover. We'll start with just a basic definition. A lot of people trip up on this. So this is an important, laying out your braced wall lines is part of the art, but also part of where you can gain some real efficiency in meeting the code. But there's some art to it, and that starts to show up in the definition. It's a straight line through the building plan that represents, it not is, but represents the location of lateral resistance along a given wall line or facade of a building, or even through an interior series of walls in the building. And it's generally, you're going to have all your exterior walls or sides of the building are going to be identified as braced wall lines. And then the question becomes, do I need to kind of fit in some interior braced wall lines so I can have enough window openings on a given wall, or it's just I'm in a high load area, I need that interior wall regardless. Those are decisions that you would make along the way, and it's one of the first decisions you make. The code gives some ideas of how the text plays out on a couple example plans. The right being the upper story of a two-story plan. You see that's a fairly simple box, and so there's three braced wall lines front to back, and just two that are required left to right on this plan on the upper story. So fairly simple. The bottom story has got more of an L-shaped pattern. It's got a garage exterior wall that then turns into an interior wall, and you can see the actual interior wall that this braced wall line is representing. The actual interior walls that are going to be designed either with a gypsum bracing system, or sometimes you even have to add structural panels to the interior. They're not actually on that wall line. Some people say, well, that's imaginary. I said, exactly. But it's imaginary to the extent that it represents these walls. They're close enough to it. So as long as they're within 4 feet of anywhere you draw this braced wall line, then they are considered to be represented by that braced wall line, that dotted line through the plan. And you can see the actual two interior walls may be separated from each other by as much as 8 feet. But if that wall is right in the middle between them and lines up with this wall, then they can all be grouped as a single braced wall line. There's advantage to that. And then because now you don't have to locate braced wall panels within each of those segments within certain spacing requirements that the code has. So you can see here the same thing's done on this back wall in this building. Braced wall line 1, the left to right or east to west braced wall line is capturing all these jigs and jogs in the braced wall line, but its actual dotted line doesn't align with any one of those portions. So a lot of people get tripped up on that. Sometimes even code officials say that you can't do that, but the code clearly you can do that, and there's good reason for it, because we're representing the net effect of all these closely associated wall lines that are oriented in this direction to resist wind load that's pushing on the building from left to right, or seismic response. These braced wall lines can only be spaced a maximum of 60 feet apart to be in the prescriptive scope for wind, and 25 to 30 feet with some exceptions to go more in certain conditions for seismic bracing. So it requires you to break up your building and provide some walls of resistance, and not become too huge and then fall outside of the scope of the way these provisions were put together. Braced wall panels, that's a full height section of wall from plate up to that plate, or from floor to ceiling. It's not interrupted by openings, so it's able to drag the shear force from the top plate and a floor or roof above down through the framing system into the bottom plate, where then it's transferred into the next assembly below, whether that's a floor or foundation. So it's got to be a full height panel, and that's what provides the racking or shear resistance to a braced wall line. Braced wall panels are constructed using one of the many bracing methods that we'll talk about later. Here's an example of how they would get laid out on these wall lines, the front and back, left and right wall lines that are folded out, so you can kind of see them in plan view, what those walls look like. And you can see this one back here has 2 braced wall panels. The braced wall panel has to be at least 10 feet from the end, although you can get around that. You can space it further. If you hire an engineer to just look at the collector up here and make sure you're not overloading your splice joints or whatever in your top plate, you can get around that. But that's a prescriptive limit in the code. And the braced wall panels, for the sake of having a uniform distribution of shear resistance going down to the foundation, they have to be spaced apart no more than 20 feet max to be within the scope of the prescriptive code. Again, if you run into a problem with that, there's ways of engineering around it. You would have to have that particular portion engineered. The width of the braced wall panels, depending on the bracing method, the minimum width you need to meet. But obviously, most of the time, you would fill that entire width with a braced wall panel, and you would just have more bracing than you need. And again, the amount of bracing you need on a braced wall line depends on where it's at in the building and how big the building is and what your wind and seismic loads are. But this just shows the basic requirement for how you've got to meet in spacing the panels that you are using, the braced segments of the wall along the length of a given braced wall line. Continuous sheathing also has to have braced panels within its length between window and door openings, even though it's continuously sheathed above and below. But that continuous sheathing above and below the openings is just to make sure those brace panels are anchored a little better and provide a little higher strength. That's why you get the advantage out of the continuous sheath. It creates more of a system that helps anchor these panels that are actually the portions of the wall that are dragging the resistance through the wall assembly. All right, so and in fact, the continuous bracing method was based on research that I had done to develop that methodology and bring it into it was brought into the first draft of the International Residential Code. Minimum required length of bracing per braced wall panel. So you have to basically there's a set of tables. These are pre-calculated that are tabulated bracing lengths. Those are sort of tabulated for standard conditions, a standard kind of roof slope or roof height above, eave to ridge height, a standard wall height, so that we can calculate bracing amounts for a standard set of conditions. But if you've got a lesser roof slope or a greater roof slope, there are adjustment factors you need to apply. And they can actually help you. If you've got a more efficiently designed building, or say you have 9-foot story walls and 8-foot story walls in the second story, there's a factor that would then reduce your bracing amount required because you've got less wind or seismic load based on the actual configuration. So those tabulated bracing amounts, that is your starting point, are somewhat conservative. Many buildings, there will be adjustment factors you can apply that would reduce your bracing amounts needed, and we'll look at that a little later. As I mentioned earlier, only wind bracing needs to be checked in the low seismic categories, what are known as seismic design categories A, B, C. For townhomes, however, in this moderate seismic design category C, you would also need to check seismic bracing in addition to wind and find out which one actually requires more bracing in each given wall line. So a little more work when you get into the high and moderate seismic areas with townhomes. And then for single family homes, that seismic check only kicks in when you get into the much higher seismic conditions, which are known as seismic design category D. And that's sort of broken into 3 different levels, D1, D2, and D3. But we don't need to worry about getting into that today. So here's an example of the tabulated, sort of the default basic bracing amount values for all the different bracing methods listed here in the columns of the table. So based on your building configuration, let's say you're looking at the top story of a 3-story, top story of a 1-story, or the story of a 1-story building. Then you would look at these category of rows to determine your bracing amount. Let's say your braced wall line spacing between 2 braced wall lines in a given plan direction that are sharing load is 30 feet. You would look through this row, and if you're using, say, a wood structural panel, intermittent panel spaced along the wall, not a continuous sheathing, then you would need 5.5 feet minimum of bracing. The code also says you need a minimum of 2 brace panels. So, and the minimum brace panel is 4 feet, so you actually end up with 8. So, but this is your minimum bracing default amount to which you apply some adjustment factors that are in this table. And you could end up with more than 8 feet with all these combined adjustment factors, or less than the tabulated amount, depending on your building configuration. And so the adjustment factors fall into 8 different types in this table, depending on your conditions. They address wind exposure, which has a huge effect on your bracing amounts, up to 50%. The bracing provisions are actually based on sort of exposure B, which is the more conservative kind of protected condition. But that's where, probably 70 to 80% of homes land in terms of in the middle of a development or in a mix of trees and development. But if you're in a more severe open exposure or a waterfront type of exposure, then there's going to be some increase in bracing. Roof eave to ridge height, as I mentioned, the roof can have a big impact on wind loads, particularly on a 1-story building, because half of your wind load or more can come from your roof. So there are adjustments to account for that here in the table. Story height, same thing of your walls. The number of braced wall lines also affect the amount of load that goes to each braced wall line. Some people see that as counterintuitive, that the way we're doing that, but the reason we're doing that is because we're considering equal shared load to braced wall lines, not a tributary geometric distribution, because that's traditionally the way engineers have handled it, but it's not right actually. These buildings act as rigid diaphragms, and the load gets distributed on that basis to wall lines. So these adjustment factors for braced wall lines were needed, and in the end, you come up with a more efficient answer in many cases than what an engineer will give you with a traditional sort of what's known as a tributary area load assignment. Then hold down brackets are there for a couple of reasons. One, for intermittent brace panels that are kind of acting alone as an individual brace panel, and you may only have foam or a non-structural fiber board next to it. That panel, then if you add some restraint to it to give more restraint in overturning, like just a simple 800-pound hold down bracket bumps up its resistance capacity quite a bit. And that then reduces the bracing amount that's needed. So you get some benefit by adding just some modest hold down brackets. No interior gypsum finish. All the bracing methods are based on having interior gypsum finish on the walls installed to the finish requirements. And that's because interior finishes have a huge impact on the lateral performance of buildings, as much as 50% or more of their capacity, particularly once you've had windows and doors and all the siding installed. It can dwarf what you consider your engineered systems. That in part is somewhat accounted for in the IRC. There's some system effect that engineers unfortunately can't use because it's not in their standards, but it's a real effect on these building systems. Is somewhat accounted for in the IRC's provisions, but gypsum is assumed as a baseline condition to be on the interior side of the wall. If you have a garage without gypsum or some other application, then you'll need to apply the gypsum adjustment factor, and you're going to bump up your bracing amounts to sort of account for the gypsum not being there. There's also the benefit of using a gypsum as a bracing method itself. And if you increase the fastening from a minimum 7-inch on center spacing for the basic gypsum bracing method to 4 inches on center, then you can get a little more capacity out of your interior braced wall lines with just gypsum. And this gets you, this can be very beneficial. I've had to actually do this on some houses that were built wrong because the bracing wasn't planned ahead of time. And this provides a simple solution just by adding additional fasteners to gypsum that's already there, remudding the wall, and you're good to go. Doesn't get you out of jail free all the time, but oftentimes that helps. Better to plan that in while you're designing and putting your plan forward than later. But there's just a lot of flexibility in these provisions. It makes it look complicated, but it's really not. And I'll show you the basic how you apply these factors. The same thing for seismic bracing. Here, though, instead of braced wall line spacing, it's based on the braced wall line length. because the seismic load is based on the amount of mass, not the area of the surface of the building, but the amount of mass, which is more floor area oriented. So it's based on the depth of the building and the load direction, which is represented by the length of the braced wall line. So just a different parameter, but that's what you use to pick your seismic bracing. And otherwise, you go in and you get your default number, and then you go to your adjustment factors for seismic bracing, which are different. Some of them are similar, but they're different. They're sort of more mass-based because we're dealing with, it's mass that creates the load. If you have zero mass in your building, there's no seismic load. Force equals mass times acceleration. Isaac Newton figured that out, and it still stands true today, even in building response to seismic. So that's what these factors account for, is different things related to the mass of the building that would affect how it responds and how much bracing you need to take care of your seismic loads. So here's the basic formula. If you can do multiplication, you can take care of all those adjustment factors. People don't like multiplication in prescriptive code, but to do bracing correctly without making it ultra conservative, and therefore in many cases not able to be used for homes where you want to have windows and doors in them, you have to have some math. And basically you just take the tabulated amount required for the bracing method you're using, and then you multiply it times each adjustment factor, times adjustment factor 1, times adjustment factor 2, times adjustment factor 3, whichever one is applicable to the geometry and conditions of your building that you select out of those adjustment tables I showed you. And they're all cumulative. So you just keep multiplying until you've multiplied your tabulated bracing amount by all of those adjustment factors. Some may be more than one, some may be less than one, and in the end, you come out with the bracing amount that's needed for that particular braced wall line on your building. And then you just have to check to say, okay, do I have that amount of bracing on that braced wall line with the bracing method I'm using and the braced wall panels the way I have them laid out and the windows and doors are arranged? And if it does, then check you're done with that braced wall line, you move on to the next one. So it's simple. It's a simple accounting process, but it does require you to look at the details of your plan and each braced wall line and go through this process. Now, one of the things you have to do is choose your bracing method, and there's advantages and disadvantages to each bracing method, and depending on where it is in the building, is it an interior wall line or exterior? Are you trying to use a bracing product that has multifunctional, or are you doing things, the old-fashioned way with this product does this product does that, this product does this, and building up your wall assembly that way? How much strength do I need? The different bracing methods have different strength, and that'll show up in the bracing amount that's needed. The weaker method is still a good method, and it may have advantages for other reasons. You just need to have a little more space on a wall line to do that. A lot of end walls, a lot of interior walls, particularly walls separating garage and indoor space, there's plenty of space there, excess space for bracing, and some of these methods are maybe more economical there. So use those on those wall lines and use a different bracing method on a different braced wall line. So the bracing methods are sort of divided into two basic categories, some of them using the same material, but they're applied differently. Intermittent bracing means you're just going to apply different panels like at different places on the wall, or it's not even a panel, it could be a lead-in brace with gypsum on the interior side, and they have to be applied to different panels or segments of the wall. And in between those bracing methods, you could put anything non-structural you wanted to, because you're just relying on those intermittent panels, not the continuity of a continuous bracing. And this works for a lot of walls and has some advantages. So there's multiple ways of doing that with different materials, the intermittent bracing approach. And then there's a couple more intermittent bracing approaches that are actually narrow panel approaches, or are treated that way. So they can be used with intermittent bracing systems on other parts of the same wall line. And then there's a host of, or four continuous bracing methods that use either wood structural panels or structural fiberboard, which is not your just regular insulated fireboard. It's a little higher density, you have higher connection requirements to get your shear capacity out of it. And then, as we mentioned earlier, based on the strength of these systems, you can make and the strength of an alternative or proprietary system, you can make a direct substitution or an adjusted substitution, an additional adjustment factor to account for the strength of that system right into the prescriptive code and substitute it for one of these bracing methods. So there's 16 in total, and 7 variants actually use wood structural panels. And of course, we see that being used a lot in practice, but there's a lot of other methods. And in fact, traditionally, 20, 30, 40 years ago, when I was building and in the construction industry, what we saw a lot of were just the old-fashioned lead-in braces still, with just the gypsum on the interior as you're bracing, and on the exterior, if you were in the north, you were using foam as part of the first sort of energy code advancement, after the oil crisis in the 1970s. So, but that's faded away. I mean, that's kind of been a loss in many parts of the country. They still do it some in Canada, but that's retained here. It's still available to do that. Intermittent bracing methods, as I mentioned, you have them spaced along a wall, continuous. You sheathe. Now we're talking sheathing systems, the entire wall area, but including above and below windows, and also in certain cases around corners to get the restraint. But if you want to switch to intermittent bracing on the wall around the corner for the loads in the other direction on the building, we'll get into details later where you can use a panel just at the end of the wall that's a little wider, or this 800-pound hold-down bracket for no other reason than to provide the same restraint a wrapped corner would provide. Whereas in that product we saw earlier, they actually provide you with a wrapped corner element, which is pretty cool. You can mix bracing methods. Of course, you can mix bracing methods from story to story, use a different bracing method on each story. You can mix bracing methods on a given story between braced wall lines. For example, you can use gypsum bracing method on an interior braced wall line on the same story that you have a parallel wall that's an exterior wall that's using some other bracing method. Within a wall line, let's say you have an interior braced wall line that in the interior building that's braced with gypsum on both sides, but as it goes to the exterior and becomes an exterior wall, it has another bracing method on it. As long as in that case, the total bracing amount along that wall is based on the weaker of the two, let's say it's the gypsum in this case, and you meet that amount, then you satisfy the intent of the code. In fact, it would be a little stronger, but that makes it simple to mix different bracing methods and have a design that's very practical and efficient. So those rules are built into the code for that purpose, to allow that to be done, but also to provide some limitations where you can get into problems with incompatibilities in the rigidity, or I'll say brittleness and ductility of bracing systems. In the higher seismic areas, there are some additional limits on not being able to mix bracing methods in some cases. So now when we talk about the different bracing methods, and I mentioned earlier that each braced wall panel or segment of wall that has a given bracing type on it or method on it, there are certain criteria and the width of that full height braced wall panel for it to be considered counted, contributing length, it says here on the right-hand column, to actually be counted as contributing some length to the length of bracing that you calculated or figured was required for that wall line. So, if your diagonal wood board or wood structural panel or structural fiber board or your particle board sheathing or your Portland cement, you can use Portland cement. It's one of the strongest bracing methods in the code. The old-fashioned 3-coat Portland cement. Your brick veneer bracing method, which needs to be used in higher seismic areas if you have brick veneer and it's a heftier wood structural panel fastening and anchoring that needs to be done. But if you're using any one of those, each bracing segment that you're going to count its length as toward that required bracing amount you calculated, it has to meet these minimum lengths along the wall or width of wall segment to be counted. If it doesn't, unfortunately, you can't count it. Now, I won't get into it. There is a separate table that gives you partial credit because, gee, what if it's not 48, it's 36 inches? I know I'm still getting some strength out of it. So we did add some flexibility in a separate table that under certain conditions, on an 8-foot or 9-foot wall, you can skinny that down to 36 inches wide and still count some bracing, but you're not going to get the full 36 or 3 feet of actual contributing length. There's sort of a little bit of a penalty there, but that's the flexibility that you even have in the intermittent bracing method to make that work in some moderately challenging conditions. And that would apply to substitute materials that are shown to be at least equivalent to any of these. And then there's an alternate brace method, which includes hold down brackets and all of those on each bracing method that have also minimum width requirements for each panel. The continuous sheath garage opening also has minimum width requirements for those garage, wall segments between the garage opening. And then the continuous sheathing is a little more complicated, but this is important. So just because you continuously sheathe your building doesn't mean you get out of jail free. That it's not a simple button. You still have to meet these minimum panel width requirements between openings based on the opening height. Otherwise, you will not get the performance out of that wall system that the code intends. So, based on the clear opening height in inches next to a given wall panel, whether it's a door or window opening, you take the worst case. So if it's a door opening, it's going to be around 80 inches or so, 82 if you add your rough opening size. You need your panel next to that needs to be at least 32 inches wide if you're 8 feet wide. Otherwise, in your continuous braced wall line, you can't count the length of that panel as contributing. Okay, doesn't mean your wall doesn't have enough bracing elsewhere, but you have to check each panel. Here's an example of some portal frame methods. Lots of fastening, sometimes some extra hardware depending on the method you're using and the strength you need and the width of panel that it allows you to get away with. But you have to follow those procedures found in this section of the code depending on which method you want to use. And I'll leave it at that. Your corners of continuous bracing methods, you can do the sort of where we started that method out back in the first 2000 edition is wrap the corner with the minimum 2-foot return panel. That's easy to do, but sometimes you want to switch to a different bracing method on the other side. So we've added this minimum 800-pound hold down bracket at the corner. You can eliminate this corner return panel and switch to another bracing method. That can become pretty handy at times. Or you can just use, instead of the minimum 2-foot wide panel that is required for the continuous bracing method at the corners, even though it may not be a contributing panel because of its width and the window height, as we saw in the earlier table, it still anchors the corner. But you could just switch up to a 48-inch panel and not have the corner return and have the same effective restraint at the end of the wall. So lots of options here, even moving that restraint from the end of the wall line and sort of creating a false anchoring end by having that hold down bracket put to the other side of a window or door that's right at the corner. And then that becomes the anchoring end of that continuous sheet braced wall line. So lots of flexibility there in the detailing. This is just showing, a simple 800-pound hold down bracket. There's a number of options that you can do, and even post install if somebody forgets to do it, or if you just want to do it that way, post install, because it's easier to locate the anchor in the right spot on the plate where the stud is that you need to anchor. That's one of the ways you can get that 800-pound bracket. You've got to be concerned about detailing your wall connections and to floor and roof assemblies or ceiling assemblies. There's multiple ways of doing that. If they're not aligned with the joist framing, then you need blocking to have the correct fastening, and that's all prescribed in this particular section of the International Residential Code, R60210.8, which deals with that brace wall panel support and connection conditions. Same thing with if you're on like a partial height foundation wall, say at a garage opening or something, and this is a braced wall panel above, then there are certain anchoring requirements on that stem wall to make sure that the loads then go down through the stem wall and get into your foundation. A lot to go over there. This is an accounting table that you can use to kind of put what I mentioned into a stepwise process. Step 1, lay out your braced wall lines. Make sure you meet that 4-foot offset allowance for that wall to represent a series of actual walls that are closely aligned, but not exactly aligned. Then step 2, you look at, document what's the support conditions, how many stories and a roof above am I supporting, because that's going to tell me where I go into the table to pick out the bracing amount. what's the spacing to the next braced wall line? Or if it's a middle interior wall, what's the maximum of the two spacings of the parallel walls to either side that are sharing the load? Or the code allows you to take the average, which is what I normally do, because that's, I think, a little more accurate, not quite so conservative. And that's your braced wall line spacing that you pick your tabulated bracing amount from. Of course, you've got to pick a bracing method that determines the amount of resistance you're getting out of the bracing method, and that affects the bracing length required. Then you get your tabulated length out of the table, and then you adjust it by that simple equation, multiplying the adjustment factors times the tabulated length. And then you check, does it, what your total required length is, and then you check that versus what you have on the wall. If it doesn't meet it, you got to adjust some things. Go back, make those adjustments over here in your counting sheet, check it again, you passed, you're done and good. Then the only thing is, are my brace panels within 10 feet of the corner? And this is an old number here, 12.5. It should be 10. Code used to be 12.5. I think 12.5 is fine, but it changed to 10. And then the code used to prescribe a spacing center to center of brace panels, but that was changed to 20 feet between, which is easier to measure and observe braced wall panels, because the center distance depends on the length of a particular braced wall panel itself. So anyway, you check those things out, all checks out, you're done. You move on to the next brace wall line, enter the information from the plan, and go through it. It's pretty straightforward. You can actually get pretty fast at this once you've gotten used to it, and you just have the plan laid out in front of you with your sort of braced wall lines. Oftentimes I'll use a magic marker or a highlighter just to lay out the braced wall lines, and then just immediately start inputting onto that accounting sheet manually. And after you've done it a few times, it does not take long, particularly in a simple building like this. It's a matter of minutes to input the conditions, like the spacing, 31 feet front to back, 44 feet left to right. It's a one-story building supporting a roof only, bam, bam, bam. Pick out your adjustment factors from the table and run your check, and you're done. This custom plan, a little more complicated, and how you break out your braced wall lines. You've got more choices there. So sometimes you say, well, this looks like a good choice for me to start with. I'm going to run with this unless something in my analysis shows I would have been better off adding another wall line, or maybe shifting it a little bit to bring something that was close to compliance but barely out. And you'll develop a feel for that through practice. And so this one, has 5 braced wall lines in either direction. Sometimes you might have 3 in one and 5 in another. Sometimes you might have 7 in one direction and 2 in another. If you've got a long row of townhouses and you're treating it as a single building in terms of addressing your wind loads, which is an advantage to do that. But there's a case where you might have many wall lines through the depth of the buildings. Some of them separate, fire separation walls, but only, sort of 2 major wall lines running down the sides of the buildings, even though they'd be individual walls in the terms of anchoring them, because you've got fire separation between one unit to another. Viewing it as a single building is the way the loads are going to actually happen, and it gives much efficiency in your design and applying the prescriptive provisions. It's a little trick there. So you select your bracing method, as I talked about. You select your tabulated bracing amount, as I talked about. You then pick all the applicable adjustment factors out of this table, as I talked about. Same thing if you have to do it for seismic. Then you check all your brace panels and add up the contributing length based on the direction that's given in this table and the width of your individual panels. And then every qualifying panel that has a contributing length, you add those lengths up. Sometimes you have to, if you just got, say, gypsum on the interior side of an exterior wall, and that's all you're relying on bracing, you actually have to, have the contributing length. It's like the same thing as doubling the bracing length needed, because if you leave out the gypsum bracing on one side of the wall, you have the resistance of the wall. So follow these procedures here and do the math as I've filled out for a particular building, all the details for a braced wall line, did the math, checked the bracing length I've provided, and just put in here, hey, that's well more than what I needed based on the calculation and the applicable adjustment factors. What I have in qualified brace panels meets it, so that's okay. I check the spacing requirements, it's okay. I've got at least 2 panels, so I meet the minimum bracing requirement regardless of the length that you calculate. So everything's good to go on that wall line, and you just proceed through every wall line, each plan direction, each story level in the building. So you might have, a table that's several pages long, depending on the complexity of your plan. And as I mentioned, you're verifying the brace panel locations. And that applies to continuous and intermittent bracing methods. You're going to verify your corner return if you're using continuous sheathing, and regardless of your bracing method, your anchoring and interconnection to wall and floor assemblies. And just as a reminder, please don't forget the wind uplift load path. That's the demise of many buildings, not bracing, but the wind uplift load path. And if at first you don't succeed, like if you're checking a braced wall line and it doesn't quite work, maybe shift to braced wall line openings just a hair if the architectural design allows you to do that. Maybe reduce the braced wall line spacing a little bit by adding another interior braced wall line to the design. And then sometimes that's just a matter of declaring it because the wall's already there. So I'm just going to go ahead and declare it. Now it's going to have the fastening on the gypsum to be actually a gypsum bracing method and not just merely interior finish that supplements the bracing on the exterior wall. Sometimes you limit the offsets so that an entire wall line fits within that 4-foot allowance for offsets, and then you don't have to have 2 separate wall lines along a given side of the building and then different end points from which you have to space the required spacing of panels, which then sometimes adds another panel that you don't really need from a bracing amount standpoint. So if you can get those offsets so that you can call the entire wall line a single braced wall line, then that'll make a wall line pass without any other change than that. So there's lots of options you can do, but if you run out of options or it's obvious, you might need to have that portion of the building engineered. So there are alternatives to use. I've mentioned some along the way. You can have an engineered solution where you've got to design, an engineered brace wall line, locate hold down brackets, get the nailing pattern on whatever sheathing the engineer is specifying. The engineer is going to stamp that, and that has to be stamped for it to be approved by the building official. The other approach is to use an alternative bracing method that has an evaluation report that already has the prescriptive substitution rules for it to be used prescriptively without an engineer. It's just the only thing that needs to happen is it be approved as an equivalent alternative. So you may see an engineer stamp for that purpose to have shown evaluation that it's an equivalent alternative, but you don't need to have that engineered stamp on every application, on every plan, because it's an approved alternative to the prescriptive procedures in the code that the code has always allowed to be applied by a builder or even a homeowner that maybe thinks they know what they're doing. That's just a right that the residential building code allows to the builder, and also building owners, as traditionally have had the right to build their own house. They just need to do it right to the code. Okay, so and then of course, you've got these multifunctional options now that sort of add a whole new dimension to integrating bracing decisions with energy code decisions and moisture control decisions, and kind of bringing that together in one package. And I think that's sort of the beauty of the age that we're in, with new technology and also improved codes and understanding these functions and how to guide them, that helps then guide innovation in products that are coming out on the market, like these multifunctional insulated bracing panels. So having said all this, it sounds like a lot. Even though the math is simple and concept is simple, there's a lot of accounting that needs to be done. So I've worked with a programming group to take this accounting process and the code requirements and put them into a free online calculator. It's now actually just a couple weeks ago been released. It's been through beta testing, and you basically can log onto it here at this URL. It's free to use. While it's shown to be at continuousinsulation.org, a requirement I have for any client is, this is not meant to sort of get an angle on the market, but help the market make a better decision. That means it needs to be generic, not product specific. It could be used for specific products, but this gets you answers that you can then make your own decision about what products to use and know that you're using them in a code compliant way. And you just put in your project details, the basic details that kind of framework some of the major factors or adjustments that are going to be considered to the project to fine tune it to comply with the code. And then there's a tab here that's not showing that you would go through then and input as many braced wall lines as you've defined on the plan based on your braced wall line layout. And it will, you select the bracing method, it will also show you alternative solutions. So if you say, oh, I could have used an alternative there, it'll show those solutions to say, if you want to change it, this other one actually does work. So it gives you more flexibility to optimize your designs in real time as you're doing the design and documenting it. In the end, you can press a button to get a PDF report that then lays out all the braced wall lines, all that you did in your entries to show that it complies with code. And you can hand that in with whether you're an engineer or not, as a means to demonstrate compliance with the code. It's a very handy tool to use, and I encourage you to give it a try. And if you find something about it you think could be improved, there's sort of a survey button you can put in and enter in what you thought about it and what you think maybe could be improved. But that's there to help go through all these steps that I just laid out. In fact, I use it now for my own design. In fact, I've gone back and rechecked a couple old designs and found a few math errors that, I mean, they weren't non-conservative errors, thankfully, but it is easy enough to make some errors in trying to keep account of all this stuff. So this tool is really a big help as long as you input the information correctly, right? Any tool is garbage in, garbage out, but this really helps you document it and then transparently see what you did in the end and easily edit it if you need to. There you go. So here's a bunch of additional resources that you might want to look at. If you're a real geek and want to get more stuff on the wall bracing provisions, there's a guidebook that's put together. It's about 90 pages long. You will also get a copy of this presentation that has a lot more detail on the slides than I shared verbally. There's a residential structural design guide that I wrote back in 2000 for HUD. That gives you a lot of engineering tricks if you're an engineer on how to do rigid diaphragm design and also how to assign what I'd say correct bracing strengths and account for some of the system strengths that the residential code recognizes now, but the engineering standards don't. There's a newer edition of this guide, but they've removed a lot of the guts that was the value, I think, of the original edition. So I would encourage you, both are good guides, but I would encourage you if you want to get some of those tricks and data and information on system effects, then you'll need to get the original edition of that guide. HUD republished it later with a different contractor. A lot of it changed. The right size wall bracing also is a helpful fact sheet. Simpson Strong Tie has a calculator that's good. It's agnostic. And it does also, if you run into a wall line that doesn't comply, it will kind of refer you to some of their pre-engineered high strength bracing systems, which sometimes you just plain need, even if you're using some other alternative bracing product, and you can integrate that with your system. So a lot of good resources there, and I appreciate your time.
In a city that's still on the 2018 code, how does this apply to me now with 2021?
Yeah, I mean, the bracing provisions since the 2009 edition have been consistent with what I just presented. It's just been some more flexibility and a few tweaks. I mentioned a couple numbers were adjusted by a couple feet or something. But in essence, what I taught today would apply all the way back to the 2009 edition of the IRC as far as bracing goes. There have been energy code changes. I think a couple steps in particular that would affect wall insulation levels. I think back in the 2010, it would have been the 2012 code. made a step, and then just recently the 2021 code has made another step. So if you're to cover more climate zones, so with improved thermal performance. So those the bracing that applies all the way back to 2009. In my mind, it applies to even prior to that, because this is at least equivalent to those prior codes. And then with the insulation decisions, it depends on what climate zone you're in, but the 2021 code is covering pretty much the northern half of the country, with continuous insulation as kind of one of the primary options prescriptively to insulate your buildings and cut down on thermal bridging and control moisture.
One of the questions too, Jay, was around the 1/8-inch gap between the panels. Is that the typical OSB expansion factor gap, or?
Yeah, that 1/8-inch gap is there to take care of material expansion and contraction. I mean, I've seen it done on projects I've done. You warn the framers, space the panels 1/8 of an inch. They pack them in tight. It happened that the panels came to the job site or were stored and picked up, got in an environment where they were very dry, and then you install them that way and they expand. And there's no way you're going to stop that from buckling and popping off the wall. So that 1/8 of an inch relieves, that stress that would form by packing the panels in tight. So that's an OSB kind of particular thing. Everything has some expansion and contraction, but different materials can handle it differently. And the propensity to buckle is also going to depend on whether you've got your framing at 16 inches on center or 24 inches on center. You're going to have a higher probability of that buckling if you don't have that gap on 24 inches on center framing.
This other question, and there's a variety of them here, but the question was around the reversibility. So does the bracing spec change if the installed foam is facing in versus out?
It should. It should, but I to be honest, I haven't looked at their evaluation report. Sometimes, I've seen products developed with it either way, obviously one of the benefits you gain from having the foam to the interior is ductility. We're not even counting for that yet from seismic resistance. I've seen that. I'm waiting for somebody to capitalize on that from a ductile response standpoint. But when you get ductility, you also lose some peak strength. So you've got to compensate for that by adding more fasteners. Now, their schedules that they've been through testing both ways for seismic capacity would account for, and the strength they assign should account for those different orientations of the panel. But all other things equal, if there's no change in fastening, having the foam to the interior should weaken the shear capacity.
The fastener penetration in wood stud change based on wind or load requirements? How far in the tip of the nail were fasteners going in?
Absolutely. Yeah. So, I mean, the prescriptive code kind of gives you a minimum fastener embedment for an assumed fastener type. That gives you a certain level of wind load resistance. That's why I was mentioning earlier, that's one of the reasons why the IRC scope is limited for things like that. You get into a higher hurricane wind zone, and those fastener embedments that the code is assuming are no longer enough. So that's just the nature of having a scope limit to a code so that it's usable and not, it's already 4 inches thick. That, covering those high wind seismic conditions would make it 8-inch thick. And frankly, that's where you probably gain a good bit of benefit from having an engineer, professionally design the building, or an architect.
And there were some questions in the Q&A, some comments about, hey, where are the professional engineers in all of this? Shouldn't all of these be designed? And I said, well, it's specific to if you can fit the prescriptive criteria. Otherwise, you need the engineer.
It's cookbook, and it's if the engineering pre-done, as long as you fit the widget within the mold that the engineering was based on. And yes, it's a little bit complicated with bracing, but that's why we have all these provisions out there. I know there's a lot of struggle with enforcement. There's a need for training. There's a lot of inconsistency and how this is being done. I'm seeing a lot of building designers. They're not engineers, but building designers that are smart folks and can understand this stuff, and they are becoming very proficient at doing these kind of, it's basically like a tax preparer. I saw one comment that said, this is like an IRS form. Man, it sure is. You are exactly right. It's a good analogy. It helps you to be compliant with a code that's trying to protect the consumer. And unfortunately, it's necessary because this is a fairly complicated. There's lots of factors that affect the loads on a building.
There was a question regarding, it says, can you use plywood bracing on the inside of the wall as well as the exterior side of the wall to make up when you don't have enough length of the required panel?
You're saying to double up your structural panel bracing on the wall line?
Yeah, I didn't quite, it wasn't
Yeah,
stated
this is
super
something
clearly.
that's a good question, and this is something that the IRC is not real clear on, and I think it needs to be clarified. The whole framing system, and remember I was talking about restraints, and all that's kind of a balanced system to the maximum capacity of the bracing methods that are in the code, the maximum shear capacity. If you're doubling those capacities, then you're doubling the need for the framing system's overturning restraint. And it won't be there if you don't add an engineered hold down bracket system. So while it seemed to make sense, oh, I just double the panel, I can have my bracing amount. There's no adjustment factor in the code for doing that prescriptively, because you will then force you will hit a limit before you get to the full strength of that double-sided wall with 2 layers of structural panels, and it'll be an overturning force limit. So that's where something you can do it, but you're going to have hire an engineer to do that. It's outside of the limits of the prescriptive code.
Do you have engineering on how heavy the cladding can be for a given screw or nail length?
That's already built in the code. It was something we foresaw coming back in 2010 or 2012 with the energy code changes. So there was a lot of research in NYSERDA and DOE, the steel industry. I worked with the wood industry, the insurance industry, and we put together a lot of testing to look at, how much can a cladding fastener take to this thick of foam or that type of foam, and what are the limits to doing that? What size screw do you need to use if you're putting furring outbound to the foam to attach your cladding to? And so all of that's in the International Residential Code now. It's also in the International Building Code for commercial buildings. And if you're lightweight cladding like vinyl siding, or frankly anything as light as fiber cement siding or less, which is about 3 pounds per square foot max, you can usually, particularly for up to an inch and a half foam, use the regular fastening pattern, and it's plenty to support the weight of the cladding.
BWL, how does it align vertically from one story to the next?
Yeah, so of course, if it's a bearing load system, you're going to have to transfer gravity loads. So there are limits of offset for gravity load transfer where you can't go any, I think, more than the depth of the floor joist and having an offset. For shear load, the diaphragms are capable of transferring those for the range of shear capacities of bracing methods. So it's mainly an issue of anchoring them to the diaphragm above and below. As I mentioned, there's detailing requirements to do that. And those diaphragms will drag load horizontally into bracing wall lines below. So there's not offset limits, although there are on the exterior walls simply because of limits on the amount of floor overhang the code allows. And then if you're in high seismic areas, there are what are known as building irregularity limits. I didn't talk about those. They're in chapter 3 of the code, kind of a weird place, but it's kind of an overarching scope limit. So they put them there that, you can't have certain irregularities in the buildings, like misalignment of braced wall panels from one story to another in the high seismic areas. But that doesn't apply to the rest of the country in the IRC.